A warm welcome to our Knowledge to Go video about laser weld monitoring. The next 5 minutes will give you an overview about function and capabilities of this technology. Let's start with some words why Faurecia is deploying this globally.
Laser weld monitoring is just one module out of Faurecia's global quality strategy, but it's one big step towards Industry 4.0.
For any welding process, the starting point for quality is to have a stable process, and this is no different here. Laser welding is a fully automated process, and with a laser monitor, we're emulating the welder's vision, replacing it with a sensor that observes the light emitted by the process as the process unfolds. The beauty of this approach is that it gives us traceable and objective measure of quality for every single weld that we produce.
As a former UAP, I would have loved to have such a tool. Instead of waiting for cutting-edge result, having my weld quality online, this would be great.
How does it work? In the typical setup of Faurecia's laser machines, the laser beam is passing through different optical elements and then performs a welding on the metal frame. This process itself is very bright, and some of this light finds its way back the same as the laser light was coming. While the laser light is reflected by the mirrors inside the laser source, the process light, due to its different color, passes through one of them and is received by a sensor. This now converts an amount of light into an electrical signal, which is recorded and stored in a computer. These signals are like fingerprints of the laser welding process, and compared with reference fingerprints that were prepared before, tell whether the process was as expected or faulty. Because the sensor is positioned inside the laser source, we only need one monitoring system per source, regardless how many laser welding machines are connected to it. A reference is typically built automatically from about 10 welds. Of course, these welds must be validated OK welds. To give a better understanding, I simulate building such a reference manually now. I choose some signals of identical welds and put them over each other in one window. As can be seen, these signals look quite similar, but in detail don't exactly fit each other. Therefore, an average signal is calculated, and one upward and one downward shifted copy of this create the limits in which any welding signal of the same welding seam must fit. The signals belong to a seam where on the backside of one of the welding partners there are dimples. We can exactly find them in the signals as disturbances. Around the dimples, our expectations about the welding quality is different from the rest. Therefore, we can adjust the width and the height of the window around these dimples. Let's have a look on one example. In this particular case, we have a weld with differently rippled signals. This is a typical image if welding fumes are interacting with a laser beam irregularly. Such deviating signals hardly can be compared with one and the same reference. Therefore, we first have to optimize our welding process. The laser weld itself is a C-shaped weld, and if process blowing is insufficient, some additional blowing devices can be added. Now these signals were recorded with additional blowing nozzles and in result look remarkably more flat, but only for the first 80% or 20 mm of the seam. How comes? In the first part of the weld, the blowing direction is in opposite or perpendicular to the welding direction, which works fine, but in the last part the fumes are pushed to follow the welding process. Therefore, the fumes still interact with the laser beam and the process is disturbed. For now, let's assume there is no more possibility for further optimization of the process. This means the reference parameters have to be adapted to the new shape of the signals. The limits now can be set narrower in the start and middle section of the weld, but have to be widened up in the last section to not get too many unjustified warnings from the system. Once the system is set up and recording, the analytical tools provide plenty of useful information. It gives statistical data that uncovers which welds need special observation and for what reason the suspicious welds were recognized. This tool is the most important to stepwise reduce the suspect rate and match it with the real scrap rate. These numbers also can be put in a chronological context using the trend analyzer. In this example, every green line marks a cover slide cleaning. If done properly, the signal strength rises immediately to the original strength. But sometimes the signal strength follows the trend, which indicates that the cleaning didn't take place, or it drops below the expected trend, which indicates that the cleaning even worsened the situation. In both cases, the operator can be identified and an additional training can be arranged. Last but not least, there is the welding group overview that gives an easy understandable feedback in real time. Weldings are instantaneously marked green, yellow or red according to the analysis of the system. Every of our laser welding lines already has or will have these monitoring systems. The system needs to be properly understood because it always will need to be adapted to the changes in our production. In any case, nobody has to manage this alone. The process and quality engineers always take decisions in teams, and the core team from Advanced Manufacturing Engineering is supporting you via WebEx, by organizing trainings, and by deeper analysis of suspect signals on our dummy system.